Hello, this is Scott Dahman of PowerWorld Corporation. In this session, we will examine Simulator's fault analysis tool. The tool can calculate parameters that result from a ground fault or a line-to-line fault at different locations in the system, such as along a transmission line or at a particular bus. Simulator can perform single-phase faults and three-phase faults. The quantities reported are steady-state quantities rather than transients. The fault types that can be analyzed include single-line to ground faults, line-to-line faults, double-line to ground faults, and three-phase balance faults. The fault analysis tool is accessed from the Tools ribbon tab. In Simulator, we will open the case called B7 Fault Example. From Run Mode, I can select the Tools ribbon and then the Fault Analysis tool. From the Initial Fault Data tab, I can specify the fault location as being at a particular bus in the system, and then I can choose the bus here on the left, or I can choose an inline fault and then select the transmission line. If I use an inline fault and then select the transmission line, I can also specify a location along that line which it occurs in percent. The 0% refers to the end at the near bus, and 100% refers to the end at the far bus. So if I wanted to place the fault in the middle of the line, I could enter a location of 50%. I can also specify the type of fault as single line to ground, line to line, three-phase balanced, or double line to ground. The single line to ground fault is going to assume a fault between phase A and ground, while a line-to-line fault is going to assume that phase B and phase C are faulted. Three-phase balanced assumes that the three phases are shorted together, and double line to ground assumes that phase B and phase C are faulted to ground. Before I run the analysis, I have to load some parameters from the Fault Options tab. I can click the button here that says Load Data, and then click Yes on the warning confirmation, and choose the file B7 Fault Example. This file reads in some sequence data and also some mutual impedances between the lines that connect bus 6 and 7. If I look at my one-line diagram here, the case is assuming that the lines between 6 and 7 are close together and have some mutual impedance. That data wasn't in the case to begin with, but I loaded it using the auxiliary file on this screen here. I can browse the data for the mutual impedances in this screen right here. If I click Load Data again as a shortcut to open the Windows Explorer, I can right-click on the file b7faultexample.aux and open it with WordPad. This file contains some of the fault data for generators, loads, branches, and then also the mutual impedance data. This is a specialized format for fault analysis data. I can also open the Model Explorer in Simulator and then scroll down on the Explorer pane to the Fault Analysis group. Expand that, then expand the Input group, and I can look at data for branches, buses, generators, and the mutual impedances. So here's the input for the branches, including the zero sequence resistance, reactance, and capacitance, and then other related fields. Here are the inputs for the buses. So if I didn't have the file to load the data in, I could manually enter it here. Once I've entered the data, I can also choose to save it back out to the specialized format for the fault data. From the Fault Options tab, I can also specify a non-zero impedance in resistance and reactance of the fault. For line-to-ground faults, this would represent the impedance between the line and ground. I can also choose a pre-fault profile to be represented by the solid power flow or the flat IEC 909, in which case I can enter some parameters here, or the flat classical profile. I'll just return to the solid power flow. Next, I will return to the Fault Data tab, and for this first example I want to specify the fault location as being a bus fault at bus 3 with a type single line to ground. When I'm finished specifying my parameters, I can calculate the fault current by choosing the Calculate button. The fault current is shown up here in the upper right. This is the current at phase A at the location of the fault. I can also look at parameters such as voltages and phase angles at different buses, and also results for lines, generators, loads, and switch shunts. Since the fault occurs at bus 3 and in phase A, the voltage is 0 at that point, and we can see that the voltages are pretty low on phase A and high on B and C. The phase angles are shown here as well. The angle is taken to be 0 at the location of the fault, and then the other angles are relative to the location of the fault's angle. I have the option also to show the results in per unit or in amps. I can also show the fault current and other fault parameters on the one-line diagram. For example, I could choose to examine what's happening on phase A. Then if I switch to my one-line diagram, the quantities shown here pertain to phase A. So I can see the voltage here at phase A, and I can see the flows on phase A going into bus 3 where the fault occurs. Similarly, I could look at phase C or phase B or all the phases. If I choose all the phases, then the one-line diagram will show a different result for phase A, B, and C. To remove the fault and to close the dialog, I can click the Clear/Close. I can also specify fault locations and launch the fault analysis tool from the one-line diagram by right-clicking on buses or on transmission lines. For example, if I wanted to place a fault on the line between 1 and 3, at say this location right here, I could right-click on the transmission line on the one-line diagram and then choose fault. This opens the fault analysis dialog and then selects the location and type based on where I had clicked. So since I clicked on a line, it's going to choose the inline fault, and it's going to choose the line from bus 3 to bus 1 at a location of 25%, which pertains to the location that I actually clicked on that line graphically. Now I can choose to calculate this fault if I wish. And I could visualize it on the one line as well. When you choose a line fault, then the one line is going to show kind of an imaginary bus at the location of the fault. And then I can see, just from looking at the flows, that they're going in to the fault location. For faults that occur in lines, I can also see the new bus that's created at the fault location shown here in the bus's results with the name fault point. I can also browse some results in matrices here, looking at positive sequence, negative sequence, and zero sequence quantities. The next few slides recap some of the features that we saw in the demonstration. So for example, setting the fault location can be done manually through the dialog or by right-clicking on a one-line diagram. This slide explains how you can select the type of fault and what is assumed for the phases for the different types of faults, and then the impedance that you can set on the Options tab. This explains the different features of the Fault Data tab inside the Fault Analysis dialog. The sequence data can be loaded from the PowerWorld auxiliary file format, as we did, or also from a PTI sequence data file. The sequence data is normally not stored with the load flow data. However, if you save the PWB file from Simulator, then the sequence data will be stored. You can also save this data out to an auxiliary file from the Fault Options tab if you wish to use it with a different case. These slides describe the sequence data that is required for the different types of devices. In our example, we loaded this data from the aux file, but you can also enter it initially in the Model Explorer. In Simulator, fault data can also be viewed by showing the dialogues for different objects such as generators, loads, and transmission lines. If I open the information dialog for this generator, I can then click on the Fault tab to view the results and then also the inputs. I can do the same for transmission lines or transformers or loads. So the results shown up here and the inputs down here. Here we can see the inputs required for transformers and loads. Any mutual impedances between transmission lines are showed on the Fault Analysis Options tab. And as we saw, the fault data for devices except for the mutual impedances can be entered on the information dialogues or through the Model Explorer underneath the Fault Inputs folder. Here is a summary of the features available on the Fault Options tab. This explains the example that we demonstrated using the bus fault in the B7 fault example case. So we open the case, then open the fault analysis dialog, and then on the Options tab, we loaded the B7 fault example.aux file. On the Data tab, we set the fault location to bus number 3 and chose the single line to ground fault. Then click the Calculate button. The results are then shown in the upper right for the fault current and the angle at the fault, and then for the 5 different sheets for buses, generators, transmission lines, loads, and shunts. And then we demonstrated how voltages and currents for different phases can be visualized on the one-line diagram. The next slide shows how the flows and field values are replaced on the one-line diagram to reflect the fault quantities. And this is the example of visualizing the bus fault at bus 3. In Simulator, if you are visualizing the faults on the one-line diagram, you can also toggle between phases using the drop-down on the Fault Analysis button on the Tools ribbon. This slide explains the calculation used for the inline faults. So it provides a temporary bus located at the fault point. In our example earlier, we chose to clear the fault when we closed the dialog, but you can also close the form just using the Close button and then leave the fault values in memory until they're manually cleared or the case is saved or closed. Also, a clarification on the fault impedance for a double line fault. This type of fault ignores the fault impedance settings that you set on the Fault Options tab and instead internally uses an impedance as shown here. One suggestion for visualizing fault results on a one-line diagram is that you might want to change the number of decimal places that are shown so that you can see the subtle differences in the per unit voltages at different points in the system. Also a note that the sequence data can be saved with the PWB format, although generally it is not saved in the raw file format or other external text file formats. This concludes this session on Simulator's Fault Analysis tool.